Well, we have a situation here with a object being suspended from a couple of wires, and we need to find the mass of this traffic light in this situation. A couple of things to know. First of all, we're going to be really focusing not so much on the traffic light itself. We're going to be focusing on this right here, where the traffic light and the wire holding it up, the single wire holding it up, kind of come together. Because if you think about it, the traffic light and this wire right here are being pulled down by gravity together, and they're acting as one object. And so we're going to focus on this traffic light and the little wire suspending it as the system. That's going to be our single object. So I'm going to start by drawing a diagram of the forces, the Freebody diagram. And keep in mind that we are going to be drawing the force diagram. So when we draw our vectors representing the magnitudes, we are going to be focusing on the force magnitudes, not the length of the wires. So to start, I'm going to, first of all, I'm going to just draw a beginning, because gravity's pulling downward, and I know this is going to be incorrect, at least in terms of magnitude, but I want to get that there just to help me remember that it's there. So then I'm going to draw a force diagram to represent this 88 newtons. And the 88 newtons is at an angle measured from the horizontal of 53 degrees. So I want to keep that in mind as I do this. And I want to be as accurate as possible. And so in order to do that, I could make a 88 centimeter drawing, but I would need much larger paper. I can make an 8.8 centimeter drawing, but even that is getting a little ridiculous in terms of size. So I'm just going to draw I'm going to cut it in half and do a 4, or I guess in half and divide by 10. So I'm going to do a 4.4 centimeter length of arrow just to represent the forces on there. And I'm going to forego the protractor right now, but a 53 degree angle would probably be fairly close to, let's just say it's a little bit more than a 45. And if I was doing this absolutely correctly, I would absolutely be getting a protractor out right now, but I'm not. So we will just draw that to estimate. Well, at least we've got the magnitude drawn to scale. Okay, so that is our 88 Newton force going up and to the right. And now we have our 66 Newton force going up and to the left, and that is at a 37 degree angle from the horizontal. So I'm going to do a little bit more shallow, closer to 45 on the other side, and I'm going to do 33 centimeters, 3.3 centimeters to 33 millimeters to represent that force. So this right here, we'll call this one here our force of tension 1. This is our first wire, and that's going to be the force on that wire. This is going to be our force of tension 2. And so we kind of have it done. In the end, we're going to have to adjust the force of gravity vector in order to accurately represent the forces on there. Right now, it's not balanced based on this drawing. So this is going to have to be redone. So I'm drawing it in pencil, and you should too. Now, our whole premise here is based on the idea of something called static equilibrium, where nothing is really moving, the velocity of everything is zero, constantly zero, and it's in equilibrium. In other words, all the forces are balanced. So what I mean by that is if I take the force of gravity, which is pulling downward, and I add it to the force of tension of the first wire, and I add it to the force of tension of the second wire, well, it's not a plus. That will equal 0. So this equals 0. And that's what static equilibrium means. That's what all the forces are balanced. When I add all the forces up, they should just cancel out. Now we have a situation here, though, where we have angles, and they're not nice angles. They're strange. They're not strange. They're just not easy to deal with. So whenever you see a situation like this, you should automatically think you're going to have to use trig. You're going to have to use SOHCAHTOA in order to solve this, and you're correct. And when we do this, now what we want to do, we want to avoid putting our components on our final free body diagram. So what I'm going to do is I'm just going to redraw the vectors outside the Freebody diagram. And I'm going to kind of scooch this a little bit down here. I'm going to draw the first angle just like this. So I'm going to draw it. It is going up and to the left. All right. And that's going to be representative of my force of tension on the first wire. Now, according to the diagram, I have a 37-degree angle on that wire, 37.0 degrees from the horizontal. So I am going to draw this in such a way that I'm going to capture that angle because I know it. I don't want to make things harder on myself than they are, but I know that this wire is pulling upward, and I know it is pulling over to the left at a certain force, with a certain force. And I know that this angle right here is my 37.0. It's going to be my theta. Okay, that's a symbol for angle. It's just a Greek letter, theta. And now here's the thing we got to remember. We got to use our brain when we do this. We could just blindly solve the entire triangle because I know this angle is 37 degrees. I know this force of tension is 66 newtons. But we don't need to solve the entire triangle. We could. In fact, it's not a bad idea. But what we are really interested in is this force of tension of the first wire in only the y direction. Because this right here is pulling up on the sine. And it's helping the other wire pull up on the sine. They're doing it together. And essentially this one and the other one, the y component of the wire vector, of the force vector, is canceling out gravity. In fact, what I'm going to do is over here, I'm going to sort of fix my equation, not fix it, but I'm going to just make it in a way that helps me out a little bit better, because I know that gravity is pulling straight down. And so I only need to work with vectors that are in the vertical direction. I only need to work in the y with y components, because the x components don't contribute here. So they are balanced, and so the x components definitely need to be canceling each other out. And if we were to solve it, we would find that that is true. But in this case, we really only need to worry about the force of tension for the first wire in the y direction and the force of tension for the second wire in the y direction. And those added with gravity will equal 0. They'll cancel each other out. And that's basically how we do it. So let's go back to our triangle, and we're going to solve for this side. So this being my theta, this is my hypotenuse, and this is going to be my opposite side. Okay, now we do have our adjacent side, but we don't care about that. As I said, the horizontal has nothing to do with with counteracting gravity or balancing out gravity. We're just going to ignore it. And so we set up our equation, we set up our problem so we could solve for our opposite side. And so we know our theta, our angle for this, is 37.0 degrees. We know that our hypotenuse is our FT1, which is 66 newtons. That's just given in the problem up here, right there. And we are trying to solve for our opposite side, which is our F of tension of the first wire in the y direction. Okay. Now, I'm going to scooch down a little bit because I'm about to run into, I'm assuming this is going to be redrawn later to be much larger. So I'm just going to leave that there. I'm going to move this down, this whole little party down a notch, and I'm going to choose my equation. Now, we have our theta, we have our angle, we have our hypotenuse, and we have our opposite side that we're trying to solve for. So if we do so ka toa, well, it seems like it's going to be so. Literally sine opposite hypotenuse, sine opposite hypotenuse. So ka is cosine adjacent hypotenuse, so we don't need that, and toa is not what we need either. So the equation I'm going to use is the sine of theta is equal to, so in other words, opposite over hypotenuse. And just so that we know that's not a 0, I'm going to put a little p there. we are trying to find the opposite side. So what I need to do is I need to get rid of this hypotenuse. And since it's being divided right now, it's on the bottom, it's the denominator. I will multiply that here, and that will cancel out. Now, whatever you do to one side of the equation, you have to do to the other side. So I'm going to also multiply the other side by the hypotenuse. And I'm going to rewrite this just to be a little more clean. So the hypotenuse times the sine of theta will give me the opposite side. All right. So let's substitute, and then we could solve this. So the hypotenuse is, do parentheses, 66 newtons times the sine of 37, we'll call that 0.0 degrees. I got a little ahead of myself. And that will equal our opposite side. And our opposite side is Ft, the force of tension of the first wire in the y direction. And so when we solve this, the force of tension of the first wire in the y direction is, and let's see, I've already solved this, 39. Plug it in your calculator, make sure you get the same answer as I did. But I got 39.7, and we'll just round it to 7.2 newtons. All right. Now, this is not our final answer, but it is important. So I like to put little fluffy clouds around it just so that I could be like, okay, this is one thing and it's important. So it's an important step. And we now have our FT1Y. So what I'm going to do is right above that, I'm going to replace this with a piece. It's an important piece of the puzzle. So FG plus 39.72 newtons plus something is going to give us 0. All right, so I'm going to leave that there. And now I'm going to draw my second angle, my second vector. And this vector is going to be 88 newtons. We've got a 53-degree angle. I sort of represented it in this direction like this. And since I'm not trying to draw a free body diagram here, I just needed something to help me visualize. I'm going to draw an arrow up and to the right to represent this force. And this is going to be my F of tension for the second wire. And just like before, I'm going to, you could go over and up, but I like to go up and over because I like to capture that angle that I am given. I know this angle is given, and I know there's some confusion because in other situations I like to start, if I start down here, I'll choose this as my angle. But that's if I don't necessarily know the angle I'm trying to solve for it. You got to do this in a situational, you got to take the situation into mind when you're solving these triangles. The fact is, it's given. And so you don't have to necessarily worry about, so this is my theta. If you want to be really complete, we call it theta 2. I'm just going to leave it as theta. So this is the situation. It's just easier to do it this way. So once again, I don't need to worry about my x component. I don't need to worry about the adjacent side, but I definitely want to find that opposite side, which is going to be called the force of tension for the second wire in the y direction. And I think I'm ready to solve it. So I'm going to list my knowns, my givens, which is 53.0 degrees for my theta. And again, where did I get that? Well, it's from the diagram right here. I'm going to get this 88 in a second. So scooch the paper back up. And so my hypotenuse, which I didn't label right there, my hypotenuse is 88 newtons. And my opposite side, the thing I'm trying to solve for, is the force of tension for the second wire in the y direction. All right, so now it turns out we are trying to solve for the opposite side again, just like we did in the other one. And so I've already figured out that sine, and I've already figured out the equation here. So I'm just going to rewrite this just like that because I don't need to, I've already figured this out. I've already done the math. I should say I've done the algebra. So I'm going to use that same equation. And when I substitute this, I'm going to get 88 newtons times sine of theta. How about if I actually write the number? So 88 times sine of 53.0 degrees will give me my force of tension for the second wire in the Y direction. All right. And I'm running out a little bit of room there, so I'm going to just write it right here. So my force of tension for the second wire in the Y direction, when I plug all those numbers in, is 70.2, and we'll round it to 8 newtons. So once again, it's not my final answer, but it is important, so I like to put fluffy clouds around that. Okay, so I just calculated both the Y vectors. So I'm going to go back up to my little equation here, and now I could put this number in. Force of tension for the second wire in the Y direction is 70.28 newtons. And when I take those all into account, they have to equal 0. So the force of gravity plus these two numbers has to equal 0. So when I add these two numbers up, I end up with 110 on the dot, 110 newtons. So the force of gravity plus 110 newtons has to equal 0. So if I subtract those numbers from both sides, it turns out that the force of gravity has to equal negative 110 newtons. All right, and this is a fluffy white cloud as well because that's important. Now, the negative sign you get, remember, when you're dealing with vectors, negative will typically indicate direction. Since this is gravity, it kind of makes sense that it is negative because we typically call that down by convention. Down is negative. It also makes sense because the positive numbers we're pulling up, and in math, a negative number is an opposite of a positive number. So the opposite direction, opposite sign, it all works really well. Now, two things happen right here. If the question was asking for the weight, you would pretty much be done. I would rewrite that as the weight is 110 newtons, like down, if you were answering that, because we don't like to deal with negative numbers. But if it was asking for the weight, so you gotta be careful because sometimes questions do just ask for the weight and you'd be done. Okay. Now, one thing this question is not asking for is to draw an accurate free body diagram, but I'm all about accurate free body diagrams when we have a chance. Okay, so I'm going to take a little slight detour and we're going to update our free body diagram from before. So I know now that this force of gravity should be 110 newtons, and I drew these at a scale where 1 millimeter is 1 newton. So what I need to do is I need to draw this downward arrow, let me find my thingy, at 110 millimeters. So yeah, oh wait, nope, how did I do that? Nope, half that. So half 110, so 60. I need to draw 60 millimeters. So that's actually a little bit doable because otherwise it was going to go down into a lot of work that I was doing. So I'm going to draw this straight down, and 110 is half of that is, right? No, 55. That doesn't sound right. So 55 is now my force of gravity, which that looks a little bit better because if I were to draw the vertical components here, I could, and you could really just draw them right here, and that's how I showed you on the board, and then you just erase it when you're done if this is your final free body diagram. So this vertical component here plus this vertical component here adds up to equal and cancel out the vertical component of gravity. So that is a more accurate free body diagram. I didn't use a protractor, so the angles are probably slightly off. Not probably, they are slightly off. So when you actually do this, you're going to want to use a protractor if you're drawing an accurate free body diagram. But that's not what the question is asking. The question is asking, what is the mass of the traffic light? Well, why did we find the weight? Well, we were given all these forces, and so we really could only find the weight. But what we can do now is we can use the Newton's second law equation, F equals ma, and the alternative version of that of Fg equals mg. So the force of gravity, also known as the weight, because that's what gravity, or that's what weight is. Weight is the force of gravity, is equal to the mass times the acceleration of gravity, negative 9.8, or 9.8 meters per second downward, or 9.8 newtons per kilogram downward. So I am going to rearrange this. I'm going to divide both sides. I want to get mass by itself. So I'm going to divide this by G. That'll cancel out G. And whatever I do to one side, I have to do to the other. So it turns out mass is equal to the force of gravity divided by the acceleration of gravity. So if I rewrite this, mass is equal to force of gravity divided by gravity. We are almost done. So I'm just going to plug in my numbers. I'm going to substitute my numbers that I've got. The force of gravity I've got is negative 110 newtons. Now, when do I use negative 9.8? When do I use 9.8? Like I said in class, if you are dealing with direction, which we often are, you should use the appropriate indicators for that direction. And since we apparently have an indicator of direction here, we should definitely indicate the direction of gravity. And the gravity causes an acceleration downward, which is our negative 9.8 newtons per kilogram, or meters per second squared. Either one is acceptable. As I showed, newtons is made up of the units that would cancel out kilograms, and you'd get meters per second squared. Regardless, when we do the math here, it turns out that our mass of our sine is 11.22 kilograms. Okay, newtons will cancel out. Kilograms is on the bottom of the bottom, the denominator of the denominator, and that means it comes up to the top as the final unit, and that is the mass of the traffic light.